The final concept that we're going to learn in lesson 2.3 is the factor theorem. The factor theorem is a special case of the remainder theorem. The remainder theorem said if you evaluate f at c, it's the same thing as you will get if you take the function divided by the linear factor at c, and those remainders will be the same as the value of the function evaluated at that c. So here's the result here. If you use the remainder theorem to evaluate f at c at x equals c, and the result is f at c equals 0, then you know that c is a 0 of the function, and that x minus c is a factor. And that is the true value of what we're doing here. When it all comes down to it, we're using the long division, we're using the synthetic division, we're using the remainder theorem, we're using the factor theorems to help us factor larger and larger polynomial functions and solve them. For years we've been doing quadratic functions. We dabbled a little bit in cubic functions last year. And now we're saying let's expand this idea so that we can factor and we can find the answers to larger polynomials, 4th degree, 5th degree, 6th degree polynomials. We're going to use the techniques that we've just been learning, the long division, the synthetic division, the remainder theorem, in particular this factor theorem, to help us find those. So the key concept here is the factor theorem. And it says a polynomial f at x has a factor of x minus 3 if and only if f at c equals 0. So if we think that x minus c is a factor, then we can put in its related 0 into the function, and if this related 0 gives us an answer of 0, it tells us an input that will create an output of 0. Therefore, there's where the name, we've just found the 0 of the function. We've found the input that will create an output of 0. So that's our key concept from the factor theorem. You can see that you can use the synthetic division to help us find the factored form of these polynomial functions, and that's what we're going to be practicing next. They have a nice little summary of this concept. It says if r is the remainder obtained after synthetic division of f at x, so if r is the remainder, and you're taking some function f at x and you're dividing it by some linear function x minus c. If you're doing that, then the following statements are true. If r will always be the remainder, and it's the same as the value of f at c. So in your long division or in your synthetic division is what they're saying, r is the remainder. It should be exactly the same as the value of f evaluated at c. But if our remainder is 0, then x minus c has to be a factor of f at x. In essence, it goes in there evenly without a remainder. If r is equal to 0, then c is an x-intercept of the graph. So we're relating our factor back to the x-intercepts. And if r is equal to 0, then x equals c is a solution or a root of f at x equals 0. So if r is 0, we know that x minus c is a factor. If x minus c is a factor, we then know that c is an intercept, x-intercept. If it's an x-intercept, then we now know that x equals c is a solution or a root of the function. So let's see how this all plays out in our practice problems here. Use a factor theorem to determine if the binomials given are factors of f at x, and then use those binomials to see if those factors can be used to rewrite it in factored form. I also included a graph of these. I want to kind of support what we're doing algebraically with the visual, the graphical. So what we're supposed to do is use synthetic division to help see if x minus 2 is going to go into 3x cubed minus x squared minus 22x plus 24 evenly, because if it goes in there evenly, it will be a factor. So I look at the graph, and I know the graph is a little bit small, but it looks like it goes below and comes back and touches it at 2. So we're going to see if it comes out even, then x minus 2 is a factor. That means then that x equals 2 is an x-intercept. If x equals 2 is an x-intercept, that means x equals 2 is a solution or a root. And that means that we can depress this function from a cubic down to a quadratic. So our related 0 is 2, so we know we're going to be dividing by 2 into, make sure it's in standard form, 3, 2, 1, 0 it is. So I got a 3, a negative 1, a negative 22, and a positive 24. We want to draw that line underneath, bring down our first term, and now it's always multiplying at 3 times 2 is 6. We add, that is 5. 2 times 5 is 10. We add these, that's a negative 12. 2 times a negative 12 is negative 24. We add them, we get a remainder of 0. Because we have a remainder of 0, we now know that x minus 2 is a factor of this function. So that means x minus 2 times, now our depressed polynomial will be 1 degree smaller. So it was a third degree polynomial, so now it's going to be a second degree polynomial. It's 3x squared plus 5x minus 12. And now we have it as two factors. Okay, so we just got done doing that. Now they want us to see if x plus 5 is a factor. Well, if x plus 5 is a factor, then we have to go clear over here and find x plus 5 on the graph. Since it's cubic, we know it starts low to high and finishes. It can only cross the axis 3 times. It already has. So we're probably pretty certain that we're not going to get a remainder of 0. So we got our negative 5 is our related 0. We put in our 3, our negative 1, negative 22, and positive 24. So draw the line, and we bring down our 3. Negative 5 times 3 is negative 15. Add them is a negative 16. Negative 16 times negative 5 is a positive 80. 80 and a negative 22 should be a positive 58. Negative 5 times 58, that should be 40. Carry the 5 to 90. That'll be negative. Add them. What I really care about is I'm not getting a remainder of 0 here. So if I take 290 minus 24, just being careful with this, I got a 6. An 8 gives me a 6, and I get 266 as a remainder. If this does not come out as a 0, it is not a factor, which means our graph cannot cross at the related 0 of x equals negative 5. Okay, so one of the things I should have done very early on, and I'm going to try to reverse all this if I can. Okay, right there. Once I knew that x minus 2 was a factor, we depressed this polynomial. It was a third degree, now it's a second degree. We can use our normal factoring strategies to try to come up with the other intercepts and the other factors and the other x-intercepts that are on our graph here. So what I want to do is I want to factor 3x squared plus 5x minus 12. So I know that the only factors of 3x squared are 3x and x. There are factors of 12, and I can use 1 and 12, 2 and 6, and 3 and 4. So one of these combinations has to give me a 5. So I'm trying to search for that combination of 5, and I think I've got it. I think if I put a 3 there and a 4 there, the signs have to be opposite, so I want to make sure that I have a plus 3 and a minus 4 there. I'm just double checking. I can see that the outermost ones is a negative or a positive 9x, and the innermost ones is a negative 4x, and therefore I'm getting the positive 5x. So I factored that correctly. So now here's part of the goal of what we're trying to do in here is we're trying to get every one of these polynomials of a degree higher than 2 factored into linear terms if it can be. So now what I know from my graph is that the related 0 was 2. Yep, it sure looked like that was on there. The related 0 on this one, remember the related 0 is what 3x minus 4 equals 0, which means 3x equals 4, which means that x equals 4/3, which practically would mean it's approximately at 1.3 or 1 1/3 exactly. So if we could picture this graph and blow it up a little bit more, this mark in here might be at 1 1/3, and you can double check that on your graph if you want. And then our third factor was x plus 3, so the related 0 is at a negative 3. So we're really using synthetic division to help us determine if a factor is going to go into that polynomial evenly, and then we can break it down into smaller linear factors. So we're going to apply that same strategy on this last problem here. We have 4x keeps us going. I'm going to do synthetic division, so I want to divide by the related 0. The related 0 on this one is 6, and then I want to pull out the coefficients. They're in standard form 3, 2, 1, 0. So I want to pull out the 4, negative 34, the 54, and the 36. Now these numbers are getting bigger, so I might have to pull out the calculator here so I don't make any crazy mental errors. So always start this off, the process, by bringing down your first number, then it's multiplication, add. There's 24, add to the 34, that gives us a nice, neat negative 10. 6 times negative 10 is a negative 60. Negative 60 plus 54 is a negative 6. 6 times a negative 6, that's a negative 36. When we add, we get a remainder of 0. Oh, that's awesome, because I got a remainder of 0. I know that this x minus 6 is a factor, so x minus 6 has to be a factor. The depressed one that I have here is 4. It was a third power, so now, or third degree, so now it's going to be a second degree polynomial, minus 10x minus 6. Now, there's really no reason for us to do anything else with that other than take this and factor it. So x minus 6, what I know factors out of a 4, 10, and 6 to make our factorization easier would be a 2. So I'm going to pull out a 2. If I divide everything by 2, I get a 2x squared minus 5x minus 3. Then I'm going to try to factor the trinomial into two binomials. So our 2x squared has to be 2x and x. Signs have to be different, so I know that one is plus, one is minus. I'm not exactly sure where the plus and the minus go at this point. And the only factors of 3 are 3 and 1. So I'm pretty sure I want the 3 to be negative and the 1 to be positive, because there's our negative 6x and there's our positive 1x. So I've got the factorization done correctly. Oh, I'm going to redo that. I'm hitting the wrong buttons all over the place. Sorry. Close that up. I wanted just to redo that so I didn't have to retype it all. So here is our factorization of the polynomial that we started off with. I know now, because I'm just going to rewrite it so it's a little bit more clear. Hopefully write it correctly. X minus 6, 2x plus 1, times x minus 3. If we took all those and multiplied them together, we should end up with the original polynomial that we had, which was right here, 4x cubed minus 34x squared minus 34x squared plus 54x plus 36. You multiply these together, you're going to get the exact same thing that we have over here. We're just writing them in a different form. What advantage is it for us to get in a different form? When they ask us to solve this as an equation, when we solve polynomials of any degree higher than 1, so second degree on higher, we want one side to equal 0. We want to find the inputs that will create an output of 0. And now they're easy. We can pick them up. If I put in a 6, 6 minus 6 is 0. 0 times anything is 0. The other solution would be if I put in x as a negative half. So if 2x plus 1 is the factor, negative half is your related 0. If x minus 3 is your factor, then our 0 is 3. So we end up with 3 solutions to this. And our 3 solutions that we have relate back to our 3 x-intercepts, one that's here, one that's here, and one that's here. And it looks and it appears that all 3 of them are lining up. Okay, so if we go by the book here and how they want us to do that, so they want us to show and verify that each of those factors ended up using synthetic division would give us a remainder of 0. So I'm just taking this out. I'm going to go back and show you that if you would have used the x minus 3 first, just because the x minus 6 came first, maybe someone will want to do the x minus 3 first. So if x minus 3 is the factor, 3 is the related root. Bring down the 4. 4 times 3 is 12. 12 and a negative 34 is a negative 14. How about 24? Wow. How about I actually subtract those the right way? That's a 2, 22, negative 22. 3 times negative 22 is a negative 66. A negative 66 and 54 should be a negative 8. 66, 54. Wow, the subtraction is getting me at this hour. So how about a negative 12? And 3 times a negative 12 is a negative 36, so that would give us a remainder of 0. So if we add that, our remainder is 0. we have an x minus 3 as our factor. Our other factors would be 4x squared minus 22x minus 12. And then what we could do is say, all right, we've got it broken down to a second degree polynomial. Second degree polynomials, we know how to factor those. They each have a common factor of 2. Pulling out the 2, and now I've got 2x squared minus 11x, then minus 6. And then I would have to factor this into two binomials. Shouldn't change our answer one bit. We should get the same result. So 2x and x has to be plus and minus, and then you got to use factors of 6. So we need a negative 11. So 6 and 3. Our factors of 6 will be 3 and 2. 6 and 1. How about 6 and 1? So we go x minus 6, 2x plus 1, and that should equal our original function that we had, our 4x cubed minus 34x squared plus 54x plus 36. Our same roots should show up. The same solutions. Our related factor is x minus 3. Our solution has to be 3. If 2x plus 1 is a factor, then a negative 1/2 has to be your 0 or your root, and x minus 6, that means 6 is your solution. So the goal is to get it factored into linear terms so that we can take these linear terms and apply our zero factor theorem to solve these equations. So we're taking steps towards being able to solve polynomial functions through the tools of synthetic division, remainder theorem, the zero factor theorem, and the related zeros.